There is a moon in our solar system, almost exactly the size of Mercury. It is 4 billion years old. Its surface has not changed since the early history of the solar system. For 400 years, scientists looked at it, flew spacecraft past it, and called it the boring one, the hunk of rock and ice, the ugly duckling. They were wrong. In January 2025, researchers at NASA's Jet Propulsion Laboratory reanalyzed decades-old data from a spacecraft that no longer exists and found something no one was looking for. Strong evidence that beneath that ancient, crater-covered surface, a liquid ocean has been quietly waiting, an ocean world sitting at the edge of Jupiter's family. And the entire scientific community spent 50 years looking at its siblings instead. If this video sparked even one new thought about the universe, a like costs nothing but helps everything for a small team trying to reach more curious minds. In 3, 2, 1, liftoff. On the night of January 7th, 1610, a man in Padua turned a homemade telescope toward Jupiter and wrote down what he saw. He saw 3 small points of light arranged near the planet's disk, 2 to the east, 1 to the west, none of them in the same position they had occupied the previous night. He kept watching over the following days. The points of light kept moving. They rearranged themselves, approached the planet, and receded from it, sometimes disappeared behind Jupiter's bright disk and reappeared on the other side. Galileo Galilei was working with an instrument no more sophisticated than what a skilled craftsman of his day could grind and assemble. Yet, within the course of a single week, he had identified 4 objects orbiting a planet other than Earth. They were doing exactly the thing that the official cosmology of the time, the Ptolemaic system, with Earth at the center of everything, insisted nothing in the universe did except travel around Earth. These were moons, other moons, circling another world. The discovery demolished the geocentric model and provided the most direct observational evidence anyone had ever collected for the Copernican view of the solar system. Galileo published his findings in March of 1610 in a short book called Sidereus Nuncius, the Starry Messenger, and the history of astronomy split cleanly into a before and an after. There are 4 moons in that story. All 4 matter equally to the discovery itself. All 4 appear in Galileo's careful positional drawings as he tracked their movements across the days and weeks of January and February of 1610. But inside that foundational discovery, a hierarchy was already forming, not by any deliberate decision, but by the simple nature of the objects themselves and the way that nature revealed itself to a telescope. Io, the innermost of the 4 Galilean moons, moves fast enough that its position shifts detectably even across a single night's observation. Its rapid orbital motion was part of what helped Galileo understand relatively quickly what he was seeing: objects in periodic, repeating cycles around Jupiter, not random background stars. Europa and Ganymede moved more slowly, but still completed their orbits in periods of only days, providing clear, dramatic evidence of regular periodic motion. And the outermost of the 4, the one with the longest orbital period, the most measured and stately circuit of 16.5 days around Jupiter, that was Callisto. In the original drama of that discovery, Callisto was the background figure, present in every scene, essential to the completeness of the picture, but never the object the eye was drawn to first, never the one moving fastest, never the one demanding immediate attention. That pattern, present, essential, and quietly overlooked in favor of something apparently more dynamic, has defined Callisto's relationship with science for 4 centuries right up until the present day. We should spend time understanding what Callisto actually is before we talk about what was done with it, or more precisely, what was not done with it. Callisto is the second largest of Jupiter's 4 Galilean moons and the third largest moon in the entire solar system. Its diameter is approximately 4,800 kilometers. To make that concrete in the most direct possible way, the planet Mercury, the innermost planet in our solar system, has a diameter of approximately 4,879 kilometers. Callisto is almost exactly the same size as an actual planet. If this object were orbiting the Sun directly rather than orbiting Jupiter, no one would hesitate to describe it as a planet. It has more than enough mass to pull itself into a spherical shape under its own gravity. Its equatorial circumference measures approximately 15,144 kilometers. Its surface gravity is approximately 1/8 of Earth's stand on Callisto, and you would weigh about 1/8 of your terrestrial weight. Drop an object from waist height and it would take roughly 2.5 seconds to fall to the ground. A person of average height on Earth who weighed 70 kilograms would weigh approximately 9 kilograms on Callisto, less than a filled backpack on Earth. Callisto is a world in every meaningful physical sense. It has sufficient gravity to retain a thin atmosphere, which it does technically what is called an exosphere, composed primarily of carbon dioxide, confirmed by the Galileo spacecraft in observations from 1997 and announced to the scientific community in 1999. Trace amounts of molecular oxygen have also been detected in its atmospheric environment. The surface is composed of a mixture of water ice and darker non-ice material, including hydrated silicates, sulfur compounds, and various organic molecules, a chemically complex substrate that scientists have been working to fully characterize across multiple decades of observation. Callisto orbits Jupiter at an average distance of approximately 1,883,000 kilometers, completing one full revolution every 16.7 Earth days. It is tidally locked to Jupiter, meaning the same face always points toward the planet, in the same way that our moon always presents the same hemisphere toward Earth. The leading hemisphere, the face that points in the direction of Callisto's orbital motion, and the trailing hemisphere have slightly different properties, with the trailing hemisphere showing somewhat different spectral signatures due to differential exposure to Jupiter's magnetospheric particle environment and to the different rates at which each hemisphere sweeps up micrometeorites and dust in its path. What Callisto does not have is the quality that planetary scientists have historically used to allocate attention, design missions, and make grant proposals. Drama. Every characteristic that makes its siblings so compelling and so scientifically prioritized is absent from Callisto's observable profile. There are no volcanic eruptions. There is no fractured young ice, suggestive of a restless interior. There is no self-generated magnetic field. There is no young terrain. What there is, in staggering abundance, is craters. More craters per unit of surface area than any other body in the solar system for which detailed surface maps have been made. The surface of Callisto is the most heavily bombarded landscape that any spacecraft has ever photographed and any scientist has ever studied. And the reason it carries so many craters is precisely the reason the planetary science community found it so uninteresting. Nothing has ever erased them. No lava flow, no tectonic activity, no internal heat-driven resurfacing process, no atmospheric erosion of significance. Every impactor that has struck Callisto across its approximately 4 billion-year history is still recorded in the surface, preserved in the ancient ice and silicate material like fingerprints on cold stone that never warmed enough to lose them. The surface is a complete archive, a geological ledger in which every significant entry from the last 4 billion years remains legible and none of it has been crossed out. The largest entry in that ledger is a feature called Valhalla, and Valhalla is worth dwelling on in some detail because it illustrates everything that makes Callisto's surface simultaneously extraordinary and, paradoxically, easy to dismiss. Valhalla is a multi-ring impact basin, the largest of its kind confirmed anywhere in the solar system. It was first imaged by the Voyager spacecraft during their Jupiter flybys in 1979 and 1980, but the Galileo spacecraft subsequently photographed it in much greater resolution. The structure consists of a bright central region approximately 360 kilometers across, surrounded by concentric rings of ridges and troughs that extend outward to approximately 1,900 kilometers from the center of the impact. The full diameter of the ring system approaches 4,000 kilometers. If you placed Valhalla at the center of the continental United States, its outermost rings would reach from the middle of the Atlantic Ocean to the middle of the Pacific Ocean. The bright central plains of Valhalla are thought to have been created by the impact excavating and exposing cleaner water ice from beneath the darker surface material, possibly by material that flowed briefly in a near-liquid state immediately following the impact before the cold temperatures reasserted themselves and everything refroze. The surrounding rings are frozen ripples in the lithosphere, concentric cracks and troughs where the ice shell fractured and rebounded following the impact event, preserved exactly as they formed and unchanged by any subsequent geological process. A second major multi-ring structure, Asgard, measures approximately 1,600 kilometers in diameter. Beyond these two giants, the surface is covered with impact craters at every scale, enormous ancient basins hundreds of kilometers across, smaller bowls layered inside the rings of larger structures, and long crater chains formed when comets pulled apart by Jupiter's tidal forces rained down in sequential arcs of individual impacts. The longest of these crater chains, Gipul Catena, stretches approximately 620 kilometers across the landscape. The overall impression when looking at high-resolution global maps of Callisto is of a surface so thoroughly worked over by impact history that it approaches saturation, a state in which new craters can only form by overprinting older ones, because there is no uncratered terrain left to strike. This is what the planetary science community observed when they directed their instruments toward Callisto. They saw a surface that had been struck continuously for 4 billion years and had responded to none of it with any geological process of its own. That impression carried enormous weight in how Callisto was categorized and how scientific resources were allocated, because in planetary science, activity is treated as a proxy for scientific interest in a very particular and understandable way. Active worlds have processes operating. Processes mean chemistry. Chemistry in dynamic systems means reactions, products, potential building blocks of biology. A world that appears static, one that has absorbed 4 billion years of bombardment without geological response, seems to have run out of story long before any human was around to listen. The crater record is the record of what happened to Callisto from the outside. The absence of any other record is the evidence that nothing has been happening from the inside. That was the reading. For decades, that was the consensus. Understanding why that reading was so persistent and so durable requires understanding who Callisto's neighbors are. Because the comparison problem is not peripheral to Callisto's history, it is the central organizing fact of Callisto's history. Callisto has spent 4 centuries being evaluated in relation to 3 of the most dramatically interesting objects in the solar system, and that evaluation has never been kind to a world whose primary visible characteristic is that it is very old and very heavily struck. Io, the innermost Galilean moon, is the most volcanically active body ever observed by human instruments. It sits so deep inside Jupiter's gravitational well, locked into an orbital resonance with Europa and Ganymede, that forces its orbit to remain perpetually slightly elliptical, that Jupiter's tidal forces continuously flex its interior in the way a hand repeatedly squeezes and releases a ball of clay. The friction generated by this constant tidal distortion deposits an extraordinary amount of heat into Io's interior, enough to keep the bulk of the moon in a near-molten state beneath a thin, perpetually renewing crust. Sulfur and silicate magma erupt in plumes that rise hundreds of kilometers above the surface. Some of Io's active volcanic structures are large enough to be detected from Earth-based telescopes. The surface is resurfaced so rapidly by ongoing eruption and deposition that Io has essentially no impact craters. They are covered or destroyed faster than they form. Looking at Io is like looking at the most energetically live version of what geological activity means. The moon burns. Europa, the second Galilean moon, presents a fundamentally different kind of drama. Its surface of smooth, fractured water ice is geologically young in some areas, only tens of millions of years old, which in geological terms is practically contemporary. Europa's surface is crisscrossed with long, branching linear features called lineae, which are fractures and ridges produced by the tidal flexing of an ice shell floating above a global ocean of liquid salt water. The total volume of water in Europa's subsurface ocean is estimated to exceed the combined volume of all of Earth's oceans. There may be locations where that ocean vents upward through the ice shell as plumes. The scientific community has organized a significant portion of its outer solar system exploration program around the question of whether Europa's ocean, potentially in contact with a rocky seafloor where hydrothermal chemistry could sustain complex chemical reactions in the absence of sunlight, could harbor life. Europa's surface looks like the lid over a deep secret, and the secret is one of the most profound scientific questions human beings have ever asked. Ganymede is the largest moon in the solar system, larger than Mercury, larger than Pluto, and it has earned every superlative attached to it. Its surface displays 2 distinct geological terrains: the ancient, heavily cratered dark terrain that records the early bombardment history, and lighter-colored, younger, grooved terrain produced by a period of internal geological activity, during which tidal and radiogenic heating drove resurfacing and tectonic deformation. More significantly still, Ganymede has a metallic iron core, massive enough and convecting vigorously enough during some period of its history to have generated a magnetic field, a magnetosphere that is Ganymede's own, distinct from Jupiter's, interacting with the Jovian field in a complex electromagnetic environment that spacecraft have measured in detail. Ganymede is fully differentiated, has a confirmed subsurface ocean, has its own magnetosphere, and remains geologically the most thoroughly structured of the Galilean moons. In this family, Ganymede is the elder sibling with the most complete resume. Next to these 3 extraordinary worlds, Callisto brought craters, And so the scientific community treated Callisto accordingly, not with hostility, not with deliberate dismissal, but with the kind of benign neglect that accretes around things that do not immediately reward close attention in a field where close attention is expensive and the queue of rewarding problems is long. When NASA's Galileo spacecraft arrived at Jupiter in December of 1995 for the first sustained, detailed study of the Jovian system, its scientific priorities were organized around Io's extraordinary volcanism, Europa's potentially habitable ocean, and Ganymede's electromagnetic environment. Callisto received flybys, 8 close flybys, more than either Io or Europa received individually, but those flybys were driven substantially by orbital mechanics rather than scientific urgency. Callisto's position at the outer edge of the Galilean system made it an efficient gravitational stepping stone, a place where the spacecraft could use a flyby to reshape its orbit around Jupiter without burning excessive propellant. Scientists collected data at each encounter, as a responsible mission does. But Callisto was not the reason the spacecraft existed. The observations were opportunistic rather than targeted by deep scientific priority. The language that accumulated around Callisto during and after the Galileo mission reflected this status. In the scientific literature and in the informal vocabulary of the planetary science community, Callisto was described as the ugly duckling of the Galilean moons. It was called a hunk of rock and ice. It was described in scientific publications as the archetype of geologic quiescence, a phrase that appears in the peer-reviewed literature and means, translated out of professional language, that Callisto was being held up as the standard example of what a dead world looks like. This kind of language is not scientifically neutral. It shapes how a generation of researchers frames the questions they ask, calibrates the enthusiasm they bring to a dataset, and decides what deserves another look and what has already been understood. When the community has decided that something is the archetype of quiescence, the tendency is to spend the available telescope time and spacecraft bandwidth with the worlds that are the archetypes of something more interesting. But there was a problem with the quiescence label. Callisto, examined carefully rather than casually, did not behave the way a completely static, geologically featureless body should behave. The first indication of this was atmospheric. Callisto maintains a thin exosphere, a wisp of gas composed primarily of carbon dioxide. Any gas that a body as small and as poorly gravitating as Callisto manages to retain in an environment as energetic as Jupiter's outer magnetosphere will escape over time. Particle bombardment from Jupiter's radiation environment, solar ultraviolet radiation, and the simple thermal escape of molecules with sufficient velocity to exceed Callisto's modest escape velocity of approximately 2.4 kilometers per second, all work continuously to deplete any atmosphere. The carbon dioxide in Callisto's exosphere is not a relic from billions of years ago. It is being generated continuously, almost certainly by the sublimation of carbon dioxide ice trapped in the surface material, driven by ultraviolet radiation and energetic particle bombardment that break down the surface chemistry and release gaseous carbon dioxide. This is an ongoing, active, surface-atmosphere interaction that has been occurring continuously for as long as the current solar environment has been in place. Separately, trace amounts of molecular oxygen have been detected in Callisto's immediate environment, produced by photolysis, the splitting of water-ice molecules at the surface by ultraviolet light, releasing oxygen. The oxygen itself is unstable in this environment and constantly escaping, which means it too must be continuously produced to maintain even the trace amounts detected. A report published in Nature, India, in April of 2024 suggested that ozone-3 oxygen atoms bonded together may also be present in Callisto's thin atmospheric environment. This finding remains a candidate result awaiting further confirmation rather than an established scientific fact, and the script makes that distinction explicitly. It is a candidate, not a confirmed discovery. But even taken conservatively, Callisto's atmospheric environment is actively chemically productive in ways that contradict the picture of a completely inert body. The second indication of unexpected complexity came from the surface texture itself, and it is the one that sits most uncomfortably with the archetype of quiescence framing. When Galileo's cameras returned high-resolution images of Callisto's terrain, the large craters were exactly as expected: Valhalla, Asgard, the crater chains, the layered bowls of ancient impacts nested inside one another across the full visible surface. But at smaller scales, something was conspicuously absent. Impact craters below, approximately 1 kilometer in diameter, were nearly missing from the surface. Every body in the solar system, exposed to space for 4 billion years, should carry a continuous rain of micrometeorite impacts and small impactor events, which over geological time accumulates into a dense population of small pits, dimples, and shallow bowls distributed across the surface. On Callisto, that expected population was largely absent. The finest surface texture that should be there was not there. Between the large craters, the terrain was strangely smooth, as if something had worked over the surface at fine scales without touching the large-scale features, like a very fine eraser applied only to the small details, while leaving the large strokes of the drawing perfectly intact. The explanation most widely accepted in the scientific literature involves sublimation, erosion, sometimes called thermal degradation of the surface, and understanding it requires understanding what Callisto's surface material actually is. The surface is not made of a single uniform substance. It is a mixture of water ice and non-ice components, silicate minerals, carbon-bearing compounds, sulfur compounds, and various dark organic molecules, all interlocked in approximately equal proportion across the surface. Over billions of years, the ice component of this mixture sublimes transitions directly from solid to vapor under the combined influence of solar radiation, thermal cycling between day and night, and particle bombardment from Jupiter's magnetosphere. As the ice sublimes and the vapor escapes from the surface, the non-ice material that was bound up with it is left behind as a concentrated residue sitting on top of the remaining surface, a thin, dark lag deposit of non-volatile material that accumulated as the volatile ice evaporated away beneath it. This process preferentially destroys small surface features. A small crater with limited structural depth and a small volume of material to lose before it becomes unrecognizable, degrades and smooths away as its icy walls and floor sublime. A large crater with deep walls and a broad floor can lose substantial ice mass from its surfaces and still remain structurally recognizable as a crater. Over 4 billion years of this slow, continuous sublimation erosion, essentially every crater smaller than approximately 1 kilometer in diameter has been destroyed, along with the fine surface texture that those small features and micrometeorite pitting would normally produce, while the large craters survive degraded and softened at their edges and floors, but still clearly present and still clearly craters. This is a surface that is not static. The sublimation process happening today was happening yesterday, and the day before, and the decade before, and the million years before. Callisto's surface is in slow but continuous flux, driven by thermally activated chemistry, erasing its own finest-grained record while preserving the largest features with high fidelity. A world that the scientific community described as the archetypal example of geological quiescence has been quietly modifying its own surface since the early solar system through a process that requires no internal heat, no volcanic activity, no plate tectonics, just sunlight, particle bombardment, and 4 billion years of time. The 2025 study by Maria Camarca and colleagues at the California Institute of Technology adds another layer to this surface complexity. Using observations made by the Atacama Large Millimeter, Submillimeter Array ALMA during 2016 and 2017, the team assembled a global map of Callisto's thermal properties at millimeter wavelengths. ALMA can resolve Callisto's disk and measure the thermal emission across its surface in wavelengths that probe the subsurface temperature and material structure to depths that optical imaging cannot access. When the Camarca team compared the ALMA observations to thermal models of Callisto's surface, they found that no model assuming a single material with a single thermal inertia could reproduce the data. The surface requires, at minimum, 2 distinct thermal inertia values to fit the observation's 2 different types of surface material, with physically distinct properties distributed across the Moon's surface in a pattern that ALMA could detect, but could not yet fully resolve in terms of where each material is located and why the distribution takes the form it does. Callisto's ancient, uniformly cratered surface, which looks homogeneous in optical photographs, is thermally inhomogeneous at a level detectable by the most sensitive radio telescope array in existence. What those 2 materials are, whether the boundary between them reflects compositional differences laid down during accretion or produced by billions of years of differential sublimation, and how they relate to the subsurface structure below. These are questions that the JUICE mission is specifically designed to investigate, beginning with its first Callisto flybys in 2031. Piece by piece, the quiet accumulation of Callisto's anomalies tells a consistent story that the ugly duckling label was never designed to accommodate. The surface is not static, it is thermally complex. It has an active atmosphere that requires continuous generation. It may have ozone. The largest craters preserve a record of impacts that tell you what the material beneath the surface may have briefly looked like immediately after each impact: cleaner ice, mobile material, a transient liquid-like state before refreezing. The world that was filed away as geologically dead as the archetype of quiescence has been doing things to its own surface for 4 billion years that required no one's permission and attracted no one's sustained attention. All of these surface-level anomalies are interesting. They deserve the scientific attention they are beginning to receive, but they are not the most important thing about Callisto that was overlooked. The most important thing about Callisto that was overlooked is not visible on the surface at all. It is not in the craters, not in the atmosphere, not in the texture of the terrain. It is inside. And to understand what is inside and why the interior turned out to be so much stranger than the outside, suggested you have to start with a basic question about planetary physics that applies to every world in the solar system, except, apparently, this one. You have to ask, what is supposed to happen to the interior of a world the size of Callisto, and then ask why it seems not to have happened. The answer to that question, pursued through the Galileo spacecraft's gravity data and through the theoretical models that have been running on it for 3 decades, opens a door that the surface never hinted at, and that nobody saw coming when they were taking the photographs of the craters and moving on to something more dramatic. The comparison problem that governed how Callisto was treated for decades runs deeper than a simple preference for the more visually dramatic object. It reflects something structural about how science allocates attention when resources are finite and the queue of compelling problems is always longer than the time and money available to address them. Planetary science, in the decades following the Voyager flybys and through the Galileo mission, was organized around a set of questions that Europa, Io, and Ganymede addressed directly. How does tidal heating shape geologically active worlds? What does a potential ocean world look like from the surface? And can a moon generate its own magnetic field? Callisto addressed none of these questions as directly or as obviously as its siblings did. Its craters told the bombardment story of the early solar system, and that story was genuinely valuable. Callisto's ancient surface provides a reference point against which the degree of geological modification on the other moons can be calibrated. But being a reference point is not the same as being the primary subject of investigation, and in the hierarchy of priorities that drives where spacecraft are built to go and where scientists choose to focus their careers, Callisto was consistently the calibration tool rather than the target. This status produced a consequence that was not immediately apparent, but became increasingly significant as the years passed after the Galileo mission ended. The data Callisto-directed instruments had collected was less thoroughly analyzed than the data from the other moons. The Europa data drove multiple high-profile publications and funding proposals over the 2 decades following the mission. The Io data fueled a sustained program of volcanic research. The Ganymede data supported detailed modeling of the moon's magnetic environment and internal structure. The Callisto data, 8 sets of magnetic field measurements, gravity tracking from 8 close flybys, imaging data, and spectroscopic observations from those same encounters, sat in the archive and received comparatively less attention, not because the data was thought to be uninteresting, but because the resources required to analyze data deeply are finite, and the people with the expertise to analyze this particular data had been drawn to the problems that seemed more immediately pressing. Science is done by human beings working within human constraints, and one of those constraints is that you cannot follow every thread simultaneously. When a thread leads through what appears to be an empty room, you tend to set it down and follow the thread that leads somewhere more obviously inhabited. The thread through Callisto's data turned out not to lead through an empty room. It led through a room that was dark and quiet and very deep, and whose most important feature was not detectable in the first light of the initial analysis. It required someone to return to the data years later with better analytical tools and a more detailed understanding of the electromagnetic environment, and ask the question a second time. That question: what exactly is the Galileo magnetometer measuring when it records? Callisto's magnetic environment is the pivot point of the entire story. Because the answer to that question worked out across a series of increasingly sophisticated analyses, culminating in the paper published in AGU Advances in January of 2025, is that Callisto is almost certainly not the empty room that 4 centuries of observation had described. The archetype of quiescence has something inside it that nobody was expecting to find, and the only reason nobody found it sooner is that nobody had decided it was worth looking for. With the full rigor the data could support, the surface of Callisto is 4 billion years old and essentially unchanged. What is happening beneath that ancient surface is a different story entirely, one that has been quietly developing since before Earth had oceans, and that the Galileo spacecraft inadvertently recorded during 8 brief passes across a moon that the mission had mostly come to use as a gravitational tool. The data was there, the answer was there. The decision to look carefully enough to find it just took 25 years to arrive. There is a principle in planetary science so thoroughly confirmed by observation across every large body in the solar system that it operates less like a testable hypothesis and more like a background assumption, the kind of thing you start with rather than argue for. Large bodies differentiate. When a world, any sufficiently massive object, a moon, a planet, a body large enough for its own gravity to pull it into a sphere, forms through the accumulation of smaller material, the process of formation releases heat. Every particle that falls inward toward the growing body and collides with its surface converts kinetic energy into thermal energy upon impact. The interior of the growing world heats. As temperatures rise above critical thresholds in the partially melted or viscously flowing interior, physical processes that have been waiting to operate can begin. Dense materials, iron, nickel, the heavier silicate minerals become mobile and begin to sink toward the center of mass, where gravity is strongest. Lighter materials, water ice, low-density minerals, gases, become buoyant relative to the denser surroundings and rise toward the surface. The result is differentiation. The body separates itself into concentric layers organized by density, like a shaken suspension settling when left undisturbed, with the heaviest material concentrated at the center and the lightest material forming the outer layers. Additional heat during the early solar system came from radioactive decay of short-lived isotopes. Aluminum-26, with a half-life of approximately 720,000 years, was present in significant abundance in the material from which the solar system formed. As it decayed into magnesium-26, it released energy. Any body that accreted within the first few million years of solar system history incorporated substantial amounts of aluminum-26 and experienced significant radiogenic heating from within. Accretional heat from impacts and radiogenic heat from isotope decay combined in any sufficiently large body forming sufficiently early to drive interior temperatures well above the thresholds for partial melting and differentiation. The solar system's record of differentiated bodies is essentially universal among objects large enough to be spherical. Earth is differentiated: iron-nickel inner core, liquid outer core, silicate mantle, thin rocky crust. Mars is differentiated with a metallic core established by measurements from the InSight lander's seismometers. The Moon is differentiated with a small iron core formed during the magma ocean phase of its early history. Even Vesta, the asteroid, with a mean radius of only approximately 260 kilometers, differentiated completely during a brief, early window when aluminum-26 heating was intense, enough to melt even small bodies. It has a metallic core, detectable through spacecraft gravity measurements. Among the Galilean moons, Io has a differentiated interior with a dense silicate or iron sulfide core, generating the heat that drives its volcanic activity. Europa has a metallic core surrounded by a rocky mantle and an outer water ice layer that encloses the ocean. Titan, Saturn's largest moon, is differentiated. Triton, Neptune's large captured moon, is differentiated. Everywhere scientists have looked at large moons, with the precision instruments needed to characterize internal structure, they have found differentiated bodies. The process is not rare. It is the expected outcome. It is what physics predicts, and what every large body in the solar system has been found to display. And then there is Callisto. The measurement that made Callisto's interior so puzzling came from the way the Galileo spacecraft moved as it passed close to the moon during its 8 dedicated flybys. Every flyby placed the spacecraft in a gravitational interaction with Callisto that left a measurable trace in the spacecraft's velocity and trajectory. Jupiter's gravity dominated on the large scale, but Callisto's own gravity created small, precise perturbations in the spacecraft's path as it flew past. NASA's Deep Space Network tracked those perturbations with extraordinary precision using radio signals, measuring the Doppler shift of the spacecraft's transmissions to determine changes in velocity to fractions of a millimeter per second. From these precise measurements, scientists derived the distribution of mass inside Callisto, specifically how much mass was concentrated near the center versus how much was distributed throughout the body at larger radii. The key quantity derived from this analysis is the moment of inertia factor, a dimensionless number with an exact physical meaning. A body with all mass concentrated at the center has a factor approaching 0. A hollow shell, with all mass at the surface, approaches a factor of 2/3, or approximately 0.67. A perfectly uniform sphere, same density from center to surface, no variation whatsoever, has a factor of exactly 0.4. A body that has differentiated, that has moved dense material to the center and lighter material to the surface, has a factor significantly below 0.4 because mass near the center contributes less to the moment of inertia than mass near the surface, and differentiation moves mass toward the center. Earth's moment of inertia factor is approximately 0.33, reflecting its dense metallic core. Mars comes in at approximately 0.365. Ganymede, Callisto's near twin in mass and composition, has a factor of approximately 0.31, reflecting a metallic core large enough and dense enough to generate a planetary magnetic field. Callisto's moment of inertia factor, as measured by the Galileo radio tracking data and published by Anderson et al. In 2001, is approximately 0.355. That number was striking enough when it was first published to require careful reconsideration of what it meant. 0.355 is the highest moment of inertia factor measured for any large moon or planet in the solar system. It sits uncomfortably close to 0.4, the theoretical value for a perfectly homogeneous ball. It implies that Callisto's interior has very little concentration of mass toward the center. Rock and ice appear to be mixed together in roughly uniform proportions throughout the interior, from somewhere near the center all the way out to the surface, with only modest differentiation into distinct layers. This is not what planetary formation physics predicts for a body of Callisto's mass. This is not what heating by short-lived radioactive isotopes should produce. This is not what the accretion of kilometer-scale objects into a body the size of a small planet should generate. This is what you get if you somehow form a large body without ever heating its interior enough to drive the separation of dense and light material. And that, according to standard planetary formation models, should be essentially impossible. The scientific community's initial response was to examine the measurement itself with great care. Could there be a systematic error in the radio tracking data? Could there be an artifact in the way the moment of inertia was derived? One fundamental caveat was quickly identified. The derivation assumes that Callisto is in hydrostatic equilibrium, that its shape is exactly the shape a self-gravitating, rotating body of its mass and rotation rate would take if it were perfectly fluid. Bodies that are slowly rotating, like Callisto with its 16-day orbital period, can sometimes deviate from perfect hydrostatic equilibrium because their interiors are stiff enough to support non-equilibrium shapes over geological time. If Callisto's actual shape deviates slightly from the hydrostatic prediction, the inferred moment of inertia factor would be biased, potentially in either direction. This caveat has never been definitively resolved using the Galileo data alone, and addressing it is one of the primary scientific objectives of the JUICE mission's Callisto flyby program beginning in 2031. JUICE precision radio tracking will test the hydrostatic equilibrium assumption directly without having to assume it holds, and will produce moment of inertia estimates that are substantially more robust than those derived from Galileo. But, even setting the measurement caveat aside, there is no version of the moment of inertia uncertainty that makes Callisto look like a fully differentiated world. The error bars on the Galileo measurement are not large enough to bridge the gap between approximately 0.355 and the values that would indicate a metallic core like Ganymede's. Whatever corrections future measurements introduce, Callisto will remain a world that has done far less internal mass sorting than planetary formation physics predicts for a body of its size. The puzzle is real, and it has a name. Scientists call it the Ganymede-Callisto dichotomy. The dichotomy is framed as a comparison because it forces the central question with particular clarity. Ganymede and Callisto are, by every broad physical measure, nearly identical worlds. Ganymede's radius is approximately 2,634 kilometers. Callisto's is approximately 2,410 kilometers, about 8% smaller. Their bulk densities are comparable, implying similar proportions of rock and ice throughout. They formed in the same circumplanetary disk around the young Jupiter, from the same pool of material at approximately the same time in solar system history. By every naive expectation, they should have similar internal structures. And yet, Ganymede is as fully differentiated as any body in the solar system, with a metallic core, a rocky mantle, an ice shell, and a self-generated magnetic field, while Callisto appears to have barely differentiated at all. Two bodies formed from the same material in the same environment evolved into interiors as different from each other as possible. The dichotomy has been described in scientific papers dating back to the Voyager encounters as one of the most puzzling observations in comparative planetology, and a fully satisfying resolution has eluded researchers for 4 decades. Several explanations have been proposed, and the current scientific picture involves at least 2 mechanisms operating in combination. The first mechanism concerns the specific energy delivered to each moon during the late heavy bombardment, a period approximately 3.8 billion years ago, when the outer solar system underwent significant orbital reorganization, sending a wave of small bodies on collision courses with the inner solar system and the large Jovian moons. Barr and Canup at the Southwest Research Institute modeled the effects of this bombardment in a paper published in Nature Geoscience in 2010. Their analysis recognized a physical reality about Ganymede and Callisto's positions in Jupiter's gravitational field. Ganymede orbits closer to Jupiter, deeper in the planet's gravity well. Impactors falling toward Jupiter accelerate as they fall, and by the time they reach Ganymede's orbital distance, they have gained more velocity than the same impactors would have when reaching Callisto's orbital distance farther from the planet. Specifically, the impact velocities at Ganymede during the late heavy bombardment would have been approximately 20 kilometers per second, while impacts at Callisto would have been around 15 kilometers per second. Because kinetic energy scales with the square velocity, this velocity difference produces a difference of roughly 1.8 times in the energy delivered per unit mass of impacting material. Additionally, Ganymede's closer orbital position meant it intercepted roughly twice the bombardment flux as Callisto during the same period, simply because a body orbiting closer to the source of incoming material presents a larger, effective cross-section relative to the trajectories of planetesimals falling sunward toward Jupiter. Barr and Canop's models show that these two factors combine to deposit enough energy into Ganymede's outer layers to melt more than half the ice in its upper mantle. This was the critical threshold. Once that level of melting was achieved, differentiation became self-sustaining, a runaway process. As the rock and metal components of the partially melted material began to sink toward Ganymede's center, they released gravitational potential energy as additional heat, which melted more ice, which allowed more rock to fall, which released more heat. The process accelerated itself until Ganymede's interior was thoroughly sorted into distinct layers: metallic core, rocky mantle, ice shell, exactly the structure the moment of inertia measurement reflects. In Callisto, arriving at lower velocity and intercepting half the bombardment flux, the energy deposited was insufficient to cross that threshold. The percentage of ice melted in Callisto's outer layers was too small for differentiation to become self-sustaining. The process may have begun and then stalled. The rock and ice remained interleaved, more or less as they had been at the end of accretion, with only modest separation. The second mechanism, and in many ways the more fundamental one, concerns not the bombardment history but the formation process itself. The pebble accretion hypothesis, developed in a series of papers over the last decade and applied specifically to Callisto in a 2025 paper by Yuhito Shibaike at Kagoshima University, addresses the question of how Callisto assembled itself in the first place. The classical model of moon formation imagines the Galilean moons accreting from kilometer-scale solid bodies called satellite simals, which themselves assembled from smaller particles in the circumplanetary disk around the young Jupiter. When a kilometer-scale object collides with a growing body, it penetrates into the target before it is stopped, depositing its kinetic energy at depth in the interior rather than at the surface. In a body the size of Callisto, this burial of accretional energy would be expected to produce significant interior heating, raising temperatures well above the thresholds needed for ice to melt and for rock to begin sinking toward the center. Shibaike's 2025 analysis demonstrates, through detailed thermal modeling, that this expectation is not merely plausible, but essentially unavoidable for satellite-simal accretion. Every formation scenario he modeled using satellite-simal accretion produced a Callisto that was significantly differentiated. There is no version of satellitesimal accretion that keeps Callisto cold enough to preserve the partially undifferentiated interior the Galileo data indicates. The physics of energy burial in the interior, combined with the heating from short-lived radioactive isotopes present in the early disk material, drives differentiation in every plausible scenario. Satellite seamal accretion simply cannot build the Callisto the data describes. Pebble accretion changes the physics at the most basic level. Pebbles centimeter to meter scale particles drifting inward through the circumplanetary gas disk around Proto-Jupiter are small enough and slow enough, their velocities reduced by aerodynamic drag from the surrounding gas, that when they strike the surface of a growing body, they deposit their kinetic energy at the surface rather than at depth. The energy goes directly into the surface layer, where it can radiate into space from the point of impact, rather than being trapped in an interior that cannot shed it rapidly enough. The drag-reduced impact velocities also mean each pebble arrives with less kinetic energy than a large satellite seamal moving at gravitational infall velocity would carry. The combination of surface energy deposition and reduced impact energies means that pebble accretion can assemble a large body without ever accumulating enough internal heat to drive large-scale melting and differentiation. Callisto builds up cold. It stays cold. It never crosses the threshold where the separation of rock from ice becomes self-sustaining. The result is the partially undifferentiated world that the Galileo moment of inertia measurement indicates. Shibaike's conclusion is that if Jou's gravity measurements confirm partial differentiation in Callisto tested without the hydrostatic equilibrium assumption that limited the Galileo analysis, then Callisto would provide the first direct observational evidence for pebble accretion as the dominant mechanism of formation in the Galilean satellite system. Not evidence from theoretical preference or modeling plausibility, but evidence written into the internal structure of the Moon itself, preserved since the earliest phase of solar system history, and now finally becoming readable through spacecraft measurement. The implications reach far beyond Callisto. The debate between pebble accretion and planetesimal accretion as the dominant mode of solar system body formation is one of the most active arguments in current planet formation theory. It affects predictions about the composition, structure, and orbital properties of bodies in every planetary system, including the thousands of exoplanetary systems observed by space telescopes. If Callisto's interior can anchor the observational side of that debate, then the Moon that planetary scientists filed away as a calibration tool and a gravitational stepping stone turns out to be carrying evidence about one of the most fundamental questions in the field. There is one further dimension to the interior story that is essential to understanding everything that follows, because it creates the scientific tension that the next part of this documentary must resolve. The differentiation story, whether Callisto is undifferentiated, partially differentiated, how that state came to be, is a story about the interior lacking a feature. Callisto's interior apparently lacks the layered structure that standard formation physics predicts. It has less differentiation than it should. It is, in the language of the field, anomalously cold and anomalously mixed. But there is something the differentiation story alone does not answer. If Callisto formed cold and stayed cold, if its interior was never heated sufficiently to drive large-scale melting and mass sorting, then how does a subsurface ocean exist inside it? The partial differentiation model suggests an outer icy shell of perhaps 300 kilometers in thickness, formed from the modest surface warming that did occur during accretion. That outer ice shell would sit above the mixed rock-ice interior, insulating it from space. At depth, somewhere beneath that ice shell, in the zone where pressure and residual heat create conditions that require careful analysis, the question becomes unavoidable: is there liquid water? The differentiation state of the interior makes this question harder to answer, not easier. A fully differentiated Callisto, with a clear interior structure and well-defined layers, would have more predictable thermal properties and more interpretable magnetic signatures. A partially differentiated Callisto, with mixed rock and ice in the deep interior and an uncertain thermal history, is a world whose interior state is genuinely ambiguous without direct measurement. Whether there is liquid water somewhere inside Callisto is not a question that can be answered by looking at the craters or measuring the gravity or modeling the differentiation history alone. It requires a different kind of measurement entirely, one that looks not at how mass is distributed, but at how the interior responds to a specific kind of external probe. It requires a measurement of the magnetic field, and the Galileo spacecraft, during the same 8 flybys that produced the gravity data, was recording exactly that, measuring the magnetic environment around Callisto with a magnetometer that was picking up something unexpected, something that sat in the archive for over 2 decades before anyone looked at it with sufficient rigor to understand what it meant. The story of what the magnetometer found and why interpreting it correctly turned out to be so much harder than anyone initially recognized is where the real transformation of how we understand Callisto begins. The interior that should, by standard physics, be a cold, homogeneous mixture of rock and ice has been leaving a magnetic fingerprint in the Galileo data that nothing in the simple, undifferentiated story would lead you to expect. That fingerprint pointed towards something liquid, and the question of whether the fingerprint was real or whether it was being mimicked by something in Callisto's atmosphere that could produce an identical-looking signal occupied the scientific community for more than 20 years and required a fundamentally new analytical approach to finally answer. Understanding why it took so long requires understanding what the Galileo magnetometer was actually measuring and what it was measuring it against. Jupiter is the dominant electromagnetic presence in the entire outer solar system. Its magnetic field is the largest planetary magnetic field in the solar system, with a magnetosphere that extends millions of kilometers from the planet in every direction, easily encompassing the orbits of all 4 Galilean moons. Jupiter rotates once every approximately 10 hours, and as it rotates, its powerful magnetic field sweeps past each of the Galilean moons in turn. The field is not perfectly aligned with Jupiter's rotation axis. It is tilted by approximately 10 degrees, which means that as Jupiter rotates, the direction and magnitude of the magnetic field experienced at Callisto's location changes periodically, cycling through a full range of orientations roughly every 5 hours, as seen from the moon's surface. This time, varying external magnetic field interacts with any electrically conducting material on or inside Callisto. When a changing magnetic field passes through a conductor, any material with mobile charged particles, whether that is a saltwater ocean, a metallic core, or a conductive ionosphere. The changing field induces electrical currents in the conductor, and those electrical currents generate a secondary magnetic field. This secondary field, called the induced magnetic field, is oriented to partially oppose the changing primary field. It is the physical mechanism behind the law of electromagnetic induction discovered by Michael Faraday in the 19th century. Measuring the induced field at Callisto, its magnitude, its orientation relative to the primary field, and how it changes over time, provides information about the properties of the conducting layer producing it, its depth below the surface, its thickness, and its electrical conductivity, which is in turn related to the concentration of dissolved salts if the conductor is a liquid ocean. The Galileo magnetometer measured exactly this situation at Callisto. During each of the 8 close flybys, the instrument recorded the local magnetic field with high precision. The data showed that Callisto was responding to Jupiter's sweeping magnetic field by generating a secondary induced field of its own, a clear, measurable signature of electromagnetic induction occurring inside or around the Moon. The existence of this induced field was itself surprising and important. A geologically dead, fully undifferentiated ball of rock and ice with no metallic core and no internal convection should produce essentially no induced magnetic field. The fact that Callisto was producing one meant there was a conductive layer somewhere associated with the Moon, either inside it, in the form of a salty subsurface ocean, or surrounding it, in the form of a conducting ionosphere. And this is where the interpretive difficulty became severe and remained severe for over 2 decades. Callisto has a measurable ionosphere. The thin exosphere of carbon dioxide and oxygen extending above the surface contains ionized particles, molecules from which electrons have been stripped by ultraviolet radiation and particle bombardment from Jupiter's magnetosphere, producing a layer of electrically charged gas above the surface. An ionosphere is a conductor. It sits inside Jupiter's time-varying magnetic field. It will produce an induction signal in response to that field. The induction signal from a conducting ionosphere and the induction signal from a conducting subsurface ocean can, under certain conditions, look extremely similar to a magnetometer making measurements during a single flyby at a single frequency. With only a single flyby's worth of data, or even a few flybys analyzed individually, the two signals cannot be cleanly separated. Scientists examining the Galileo magnetometer data from individual Callisto flybys were forced to acknowledge that they could not definitively attribute the observed induced field to a subsurface ocean rather than to the ionosphere. The ocean was possible, so was the ionosphere alone. The data was ambiguous, and in science, ambiguous data is not publishable as a confirmed discovery. It is publishable as an uncertain observation that requires more investigation. The ocean hypothesis for Callisto was published, it was discussed, it was included in summaries of potentially habitable worlds in the outer solar system, but it carried an asterisk that never went away. Not confirmed, possibly due to the ionosphere, requires better data to resolve. For over 20 years, that asterisk sat attached to Callisto's name, while the science community focused its limited resources on Europa, where the magnetic induction signal was far cleaner and the case for an ocean was far stronger, and on Ganymede, where the mission goals were different and the scientific questions more immediately tractable. Callisto's magnetometer data remained in the archive, analyzed to the level that the then available tools allowed, and then largely set aside. The tools available in the 1990s and early 2000s were sophisticated, but they analyzed each flyby more or less independently and were not optimized for the kind of multi-frequency, multi-flyby joint analysis that turns out to be the key to separating the ionospheric signal from the ocean signal. What changed in 2025 was not the data. The data was the same data that had always been there. What changed was the analytical approach applied to it. The team led by Corey Cochrane at NASA's Jet Propulsion Laboratory recognized that Jupiter's magnetic field varies at multiple frequencies simultaneously because the geometry between Jupiter, its rotating, tilted magnetic field, and Callisto's orbital position changes in a complex pattern over time. An ionosphere and a subsurface ocean respond to these multiple frequencies differently, Their induction signatures have different frequency dependencies that reflect their different physical properties. By analyzing all 8 close Callisto flybys together rather than individually, and by examining the magnetic field data at multiple frequencies simultaneously, the Cochrane team could compare the observed multi-frequency induction pattern to the patterns predicted by thousands of different model combinations of ionosphere properties and ocean properties. Each combination of ionosphere, conductance, ocean depth, ocean thickness, and ocean conductivity produces a distinct multi-frequency signature. By finding which combinations fit the data and which do not, the team could constrain the properties of whatever was producing the observed signal. The result, published in AGU Advances in January of 2025, was the strongest evidence yet produced that Callisto's induced magnetic field is attributable primarily to a subsurface ocean rather than to its ionosphere alone. The multi-frequency analysis showed that models, including a subsurface ocean, fit the data significantly better than models relying on the ionosphere alone. The ocean explanation is, in the current scientific consensus following the Cochrane et al. Study, the leading interpretation of the Galileo magnetometer data. It is not confirmed in the sense that an orbiting spacecraft has directly measured the ice shell thickness and found liquid water underneath. It is confirmed in the sense that the best available analysis of the best available data points substantially more strongly toward an ocean than away from one. The ionosphere alternative has not been eliminated, but it has been weakened considerably as a sole explanation. The ocean, as the primary source of the observed induced field, is where the evidence points. What kind of ocean this might be, how deep it sits beneath the surface, how thick the ice shell above it is, whether the ocean is in contact with a rocky seafloor where interesting chemistry could occur, these remain poorly constrained by the current data. The Cochrane team's models explored ocean thicknesses between 10 and 150 kilometers and ocean depths measured from the surface to the top of the ocean between 130 and more than 300 kilometers. Many combinations within these ranges fit the data. Narrowing those ranges requires the more precise, more comprehensive measurements that JUICE will make during its 21 dedicated Callisto flybys, beginning after 2031. But the broad conclusion is now scientifically defensible in a way that it was not before the 2025 analysis. Callisto is very likely an ocean world. The world that was called the archetype of geologic quiescence, the ugly duckling, the hunk of rock and ice, may have been quietly maintaining a subsurface ocean. For most of the 4 billion years, it has been sitting in the outer Jovian system, accumulating craters on its surface and asking no one's permission to be interesting. The craters preserved the record of what happened to it from the outside. The magnetic signature preserved the record of what has been happening inside. Both records were there in the data, waiting to be read correctly. The surface record was read almost immediately and found uninteresting. The interior record took over 2 decades and a substantially more sophisticated analytical approach to decipher. The patience required was not Callisto's "the moon has no choice but to be patient." The patience was demanded of the scientists, and it turned out to be the most productive 25 years of waiting in the history of Jovian moon research. The interior that never sorted itself into layers, the one that formed cold and stayed cold, may nonetheless have been maintaining liquid water for 4 billion years. What kind of heat source sustains that ocean without tidal flexing? How deeply it sits beneath the ice? whether it touches the rocky seafloor where hydrothermal chemistry could operate. These are questions the differentiation story alone cannot answer. Answering them fully requires returning to the magnetometer data, to the 8 sets of measurements that the Galileo spacecraft collected during its close passes over a world everyone had already decided was not worth a dedicated mission, and to the sustained, 2-decade-long effort to understand what that data was actually saying about what exists in the darkness beneath Callisto's ancient and unbroken surface. The Galileo spacecraft entered Jupiter orbit on December 7, 1995, and it died on September 21, 2003, when mission controllers at JPL deliberately commanded it into a fatal descent through Jupiter's atmosphere. The decision to end the mission by controlled destruction rather than letting the spacecraft drift uncontrolled was deliberate and principled. Galileo had found strong evidence of an ocean beneath Europa's surface, and the possibility that the spacecraft carried dormant microbial life from Earth, the same microbes that live in the electronics, in the seals, in every cranny of a spacecraft built on a planet saturated with biology, was enough to make deliberately contaminating Europa an unacceptable outcome. So, the spacecraft that discovered evidence for 3 subsurface oceans in the Jovian system was incinerated by the atmosphere of the planet. It had spent 8 years studying. Its signal lost a few minutes into the plunge. Before that final plunge, Galileo had made 8 close passes over Callisto, getting as near as approximately 1,000 kilometers from the surface during some encounters. During each of those 8 flybys, the spacecraft's magnetometer, an instrument that measured the local magnetic field with high precision, was recording data. The data came back. It was archived. It was analyzed at a level that was thorough by the standards of the time. And then, for over 2 decades, it largely sat, not because it was uninteresting, but because the question of what to do with its ambiguity was one that the field had not developed sufficient tools to resolve. What the magnetometer was detecting at Callisto was real. The question of what was producing the detection was the problem that 25 years of theoretical development would eventually have to answer. To understand what the instrument was measuring and why the interpretation proved so difficult for so long, it is necessary to understand something about how Jupiter's magnetic field works and what happens to any electrically conducting material placed inside it. Jupiter's magnetic field is the strongest planetary magnetic field in the solar system. It is generated by convective motion of metallic hydrogen deep inside the planet. Jupiter is so massive and so compresses its interior that hydrogen at its core is in a metallic state, conducting electricity, and the convection of that conducting fluid creates a dynamo that produces the field. This field extends outward from Jupiter for tens of millions of kilometers in every direction, forming a magnetosphere so vast that if it were visible to the naked eye from Earth, it would appear larger than the full moon in the night sky. All 4 Galilean moons orbit within this magnetosphere. They are all, in a meaningful physical sense, embedded inside Jupiter's magnetic influence at all times. Jupiter rotates once every approximately 9 hours and 55 minutes, and its magnetic field rotates with it. Crucially, Jupiter's magnetic field is not perfectly aligned with its rotation axis. The magnetic pole is tilted by approximately 10 degrees relative to the rotation axis. This means that as Jupiter rotates, the orientation and strength of the magnetic field at any fixed point in space near Jupiter, including at Callisto's location, changes periodically. From Callisto's surface, Jupiter completes a full magnetic cycle approximately every 10 hours. the direction the magnetic field is pointing, the angle it makes with the surface, the intensity of the field in different orientations. All of these vary continuously and periodically as Jupiter's tilted magnetic field sweeps past the Moon. When a time-varying magnetic field passes through an electrically conductive material, it induces electrical currents inside that material. This is electromagnetic induction, the principle formalized by Michael Faraday in the 1830s and fundamental to every electrical generator ever built. The induced currents, in turn, generate a secondary magnetic field, a response field, oriented to partially oppose the primary varying field, exactly as Faraday's law of induction predicts. Measuring this induced secondary field from outside the conducting material and measuring how it changes as the primary field varies gives you a window into the properties of the conducting layer, its depth below the surface, its thickness, and its electrical conductivity. High electrical conductivity in a subsurface layer is a strong indicator of a liquid containing dissolved salts, because ions in solution are mobile charge carriers, making salt water an excellent electrical conductor. Fresh water is a poor conductor. Pure ice is an excellent insulator. A salty ocean is among the most conductive natural materials that could plausibly exist inside an icy moon. The Galileo magnetometer, during its 8 close Callisto encounters, detected exactly the kind of induced magnetic field that a subsurface conductive layer would produce. The secondary field was there. It was measurable. It was oriented in the way that electromagnetic induction would produce if there were a conducting layer somewhere beneath Callisto's surface. The detection was real, and the initial interpretation, published in the late 1990s by Khurana and colleagues and by Kivelson and colleagues at UCLA, who built and operated the Galileo magnetometer, was that Callisto might host a subsurface ocean of salt water similar to the ocean that the same research group was simultaneously inferring at Europa. That was the initial finding. The ocean world hypothesis for Callisto was born at essentially the same moment as the ocean world hypothesis for Europa. But there was a complication that did not exist at Europa to the same degree, and that complication is the reason Callisto's ocean remained uncertain for more than 2 decades, while Europa's became the organizing principle of an entire generation of spacecraft missions. Callisto has an ionosphere. An ionosphere is a layer of electrically charged particles, ions, and free electrons in the uppermost part of a moon's or planet's atmosphere, produced when energetic radiation and particle bombardment strip electrons from neutral gas molecules. On Earth, the ionosphere extends from roughly 60 kilometers to perhaps 1,000 kilometers altitude, and its ionized layers are responsible for, among other things, the reflection of certain radio frequencies back to the surface. On Callisto, the ionosphere is thin and variable, driven by Jupiter's magnetospheric particle bombardment, ionizing the carbon dioxide and oxygen in the Moon's thin exosphere. But it is measurable, and it is electrically conductive. And an electrically conductive ionosphere, embedded in Jupiter's time-varying magnetic field, will itself produce a magnetic induction signal. This is the core of the problem. The signature of a deep subsurface saltwater ocean and the signature of a thin conducting ionosphere can, under many circumstances, look nearly identical to a magnetometer making measurements during a single flyby. Both are conducting layers embedded in a time-varying external field. Both produce induced secondary fields. The geometries and amplitudes differ in detail, and a sufficiently comprehensive and sophisticated analysis ought to be able to separate them. But the analysis requires data at multiple frequencies simultaneously, data from the magnetic field varying at different rates due to different aspects of the Jovian geometry, and it requires enough flybys at enough different orbital phases and enough different positions relative to Jupiter's magnetic axis to sample the full range of conditions. Analyzing a single flyby, or even a few flybys analyzed individually, does not provide enough constraints to confidently assign the observed induced field to one source rather than the other. The Galileo mission produced 8 Callisto flybys, 8 sets of data, with the spacecraft approaching from different directions and at different phases of Jupiter's rotation, should in principle be enough to start distinguishing the sources. But the analytical tools available in the 1990s and early 2000s were not designed to perform a fully coupled multi-frequency analysis across all 8 flybys simultaneously. The data was analyzed, the ocean hypothesis was noted, the uncertainty was documented, and the scientific community moved on to Europa, where the same induction signal was unambiguous enough that the ionosphere explanation was ruled out immediately, because Europa's ionosphere is weaker and less variable than Callisto's. The Cochrane et al. Paper published in AGU Advances in January of 2025 is the first work to apply a genuinely multi-frequency joint analysis to all 8 Callisto Galileo flybys simultaneously. The key insight behind the analytical approach is that Jupiter's magnetic field does not vary at a single frequency at Callisto's location. Because Jupiter's field is tilted, and because Callisto orbits Jupiter at the same time Jupiter rotates, the relative geometry between Callisto and Jupiter's magnetic axis changes at multiple distinct rates simultaneously. The synodic period of Jupiter's rotation, as seen from Callisto, the orbital period of Callisto itself, and the beat frequencies between them. Each of these rates represents a different frequency of variation in the magnetic field experienced at Callisto's surface. An ionosphere and a subsurface ocean respond to these different frequencies with different amplitudes and different phase relationships, because their physical properties, particularly their depths below the surface, which determine the time scale over which induced currents flow and decay, differ fundamentally. The Cochrane team built a comprehensive model framework that parameterized thousands of different combinations of ionospheric conductance and ocean properties, depth below the surface, thickness, and electrical conductivity, and calculated the predicted multi-frequency induction signature for each combination. They then compared those predictions to the actual magnetic field measurements from all 8 flybys simultaneously, using advanced statistical fitting to find which combinations of parameters could reproduce the observed data. What they found was that the data is substantially better explained by models that include a subsurface ocean than by models that attribute all the induction signal to an ionosphere alone. An ionosphere-only model can reproduce some features of the data, but consistently underpredicts the amplitude and phase of the induction signal at certain frequencies. When a conducting ocean layer is added to the model at depths between approximately 130 and more than 250 kilometers below the surface, the fit to all 8 flybys simultaneously improves substantially. The ocean is doing most of the electromagnetic work. The ionosphere is real and contributes to the signal, but it does not explain the signal on its own. This result is not a confirmation of an ocean in the sense of direct physical detection. No instrument has drilled through Callisto's ice. No orbiting radar has penetrated deep enough to return an echo from a liquid interface. What the 2025 analysis provides is the strongest evidence yet derived from the available data a multi-frequency statistical argument that, across the full suite of Galileo magnetometer observations, the most likely source of the observed induced field is a subsurface ocean. The uncertainty has not been eliminated. A future analysis with different assumptions or additional data from JUICE 21 Callisto flybys beginning in 2031 could revise the picture in either direction. But the prior probability of an ocean before the Cochrane analysis was genuinely uncertain enough that scientists writing reviews of potentially habitable worlds in the outer solar system would list Callisto tentatively, with caveats. After the Cochrane analysis, the balance of evidence tips substantially toward an ocean being present. Callisto is, in the language the scientific community now uses when describing the result, very likely an ocean world. What kind of ocean world remains an important and genuinely open question, because the properties of the ocean, its depth, its thickness, whether it sits against rock or is insulated from the rocky interior by a dense ice layer, bear directly on the question of whether anything interesting might be happening in it. The physical scenario matters enormously. On one end of the range, if the ice shell above the ocean is extremely thick, perhaps 200 kilometers or more, the ocean may sit between an ice ceiling above it and a layer of high-pressure ice below it. Water, ice, at very high pressures can take on denser crystalline forms than the ordinary ice that floats on liquid water at the surface. If the ocean floor is high-pressure ice, rather than silicate rock, the ocean is chemically isolated from the rocky interior, and the hydrothermal reactions between water and rock that many planetary scientists consider the most important energy source for life in a subsurface ocean would not occur. The ocean would be cold, confined, and chemically simple. If it were inhabited, it would have to be by organisms capable of surviving on the chemical energy available from ice-water interactions and from whatever organic material might have been incorporated during Callisto's accretion, without the geothermal gradient and mineral-rich environment that hydrothermal vents on Earth provide. On the other end of the range, if the ice shell is thinner, perhaps 130 kilometers or less, the ocean may extend all the way down to the silicate seafloor. In this scenario, the radiogenic heat being released continuously by the decay of potassium-40, uranium, and thorium in Callisto's silicate component would warm the water at the seafloor, creating gentle convective circulation. Water, reacting with silicate minerals, undergoes serpentinization, a set of chemical reactions that release hydrogen gas, and the hydrogen provides chemical energy that microbial life on Earth uses at deep-sea hydrothermal environments that have never seen sunlight. The same process occurring at Callisto's seafloor would mean the ocean had access to a continuous source of chemical energy independent of any surface input, persisting for as long as the radiogenic heat continues, which, given the half-lives of the relevant isotopes, means for billions of years into the future. There is an additional dimension to Callisto's ocean that is rarely discussed in popular accounts, but matters significantly for assessing what the ocean's long-term chemistry might look like. The absence of tidal heating. Europa's ocean is heated primarily by tidal flexing, which is vigorous and ongoing. That tidal heating also drives geological activity at the seafloor, and in the ice shell it creates resurfacing, generates cracks through which ocean water might rise toward the surface, and may drive hydrothermal circulation by keeping the seafloor tectonically active. But tidal heating is also an agent of chemical disruption. It constantly remixes material, drives fresh reactions, creates new mineral surfaces, and generates gradients that can power biological processes, but also disrupt any chemical or biological system that requires stability and time to develop. Europa's ocean is almost certainly younger in its current state than Callisto's, because tidal processes continuously renew and disrupt it. Callisto's ocean, if it exists, and if it has contact with the rocky seafloor, has had 4 billion years of relative thermal stability. Absent the convulsive effects of tidal heating, whatever chemistry has been developing in Callisto's ocean, the serpentinization reactions, the slow incorporation of organic material from the silicate interior, the accumulation of reaction products over geological time, has had continuous, undisturbed time to proceed. Whether that stability is a benefit or a constraint for life is genuinely uncertain. Life on Earth evolved in an environment of constant change and disruption. But the earliest life on Earth also appears to have depended on finding protected, stable chemical environments where complex molecules could accumulate without being immediately destroyed. A stable, quiet ocean with a consistent chemical gradient and no surface disruption might be exactly the kind of environment where something complex could slowly build, or it might be a dead, chemical sea where nothing has ever crossed the threshold into self-replication, precisely because the energy gradients were too gentle to drive the process. What is clear is that the question cannot be answered by the instruments that exist now or the data currently available. It requires the ice-penetrating radar that JUICE carries on board, which will probe Callisto's subsurface to depths of several kilometers during each of its 21 close flybys, mapping structural boundaries in the ice that would reveal layering, fractures, and potentially the interface between solid ice and a liquid ocean below, if it exists within the radar's penetration depth. It requires the gravity measurements that will constrain the moment of inertia and tests the hydrostatic equilibrium assumption. It requires the multi-frequency magnetometer measurements that will extend and refine the Cochrane et al. Analysis with far more data and at far better coverage of the orbital and rotational phase space. And it requires the longest of all the perspectives available to this story, the recognition that the answer has been waiting inside this moon for 4 billion years, and the instruments now traveling toward Jupiter will be the first to ask it directly. What those instruments will find, what they will enable, and what the answer, whatever it turns out to be, actually means for how science understands both Callisto specifically and the question of where life might exist in the solar system broadly, is the question that the final chapter of this story must address. The JUICE mission's approach to Callisto deserves to be described in some detail because the scale of what 21 dedicated flybys will accomplish compared to the 8 opportunistic encounters that Galileo managed represents a qualitative rather than merely quantitative improvement in our knowledge. JUICE carries a suite of instruments designed to work in concert, each contributing a different piece of the interior characterization puzzle. The magnetometer will measure the induced magnetic field during each flyby at close distances as short as approximately 200 kilometers from the surface, and across a far wider range of orbital phases and Jupiter magnetic axis geometries than the Galileo encounters sampled. The expanded dataset will allow the Cochrane-style multi-frequency analysis to be refined substantially, narrowing the range of viable ocean depth and thickness combinations, and further separating the ionospheric contribution from the ocean contribution. If an ocean exists and has the properties that current models suggest are most likely, the JUICE magnetometer data should make the case for it essentially conclusive not technically confirmed in the way that a direct physical measurement would be, but established to a degree of statistical confidence that no reasonable scientific alternative explanation could accommodate. The gravity investigation is equally important. During each close flyby, JUICE's radio tracking will measure the gravitational perturbations Callisto exerts on the spacecraft with precision substantially exceeding what Galileo achieved. Because the tracking is performed in the X-Ca dual-frequency configuration that allows for much finer calibration of non-gravitational forces like solar radiation pressure that can contaminate a pure gravity measurement. The improved gravity data will allow scientists to determine the moment of inertia factor without having to assume hydrostatic equilibrium holds a test that will directly answer whether the Galileo measurement was biased by the past shape assumption and whether Callisto's interior is truly as homogeneous as the current data suggests. If JUICE confirms the high moment of inertia factor under the more robust analysis, it strengthens the case that Callisto's undifferentiated or partially differentiated interior is real and not an artifact. If JUICE finds a lower factor than Galileo measured, indicating more differentiation, the pebble accretion story becomes more complicated, but the internal structure becomes easier to reconcile with the existence of a liquid ocean, since a more differentiated interior would have a cleaner thermal structure and a more predictable ocean depth. JUICE also carries RIME, the radar for icy moon exploration, an ice-penetrating radar instrument capable of probing the subsurface of Callisto to depths of approximately 9 kilometers with a vertical resolution of about 30 meters. 9 kilometers is a small fraction of the 130 to 250 kilometers that the Cochrane et al. Models suggest the ocean surface lies below the outer ice. RIME will not directly detect the ocean, but it will map the uppermost layers of Callisto's ice shell in extraordinary detail, revealing the internal structure of the ice, any layering, fractures, void spaces, or compositional boundaries within the upper ice, and providing the first direct subsurface view of a world that has been imaged only from the outside. This near-surface stratigraphy will constrain models of how the ice shell was assembled over geological time and whether the shell shows any evidence of internal deformation or thermal processing that would be inconsistent with a purely conductive, undisturbed ice layer above a stable ocean. Any evidence of internal complexity in the ice, even in the top few kilometers, would be significant. The imaging and spectroscopy instruments on JUICE will also transform the understanding of Callisto's surface composition. The Janus camera will map the entire surface of Callisto at resolutions substantially exceeding the best Galileo images and will image selected regions at much higher resolution during the closest flybys, at distances as short as 200 kilometers. These images will reveal whether the surface complexity identified in the ALMA thermal observations, the two-material thermal inertia signature found by Kamaka et al. In 2025, corresponds to a visible compositional boundary at the surface. The SWI submillimeter spectrometer and the MAGIS visible and infrared spectrometer will characterize the molecular composition of the surface material in more detail than any previous instrument, potentially identifying specific minerals, organic compounds, or hydrated phases that constrain what the original accreting material was like and how it has been processed by 4 billion years of solar and particle radiation. Europa Clipper, already in transit toward Jupiter and expected to achieve Jupiter orbit insertion in April of 2030, will reach the system before JUICE and begin its own orbital tour. While Europa Clipper's primary mission is the characterization of Europa, the 50-plus close flybys that will map the surface, probe the ice shell with its ice-penetrating radar, and sample the tenuous plume material, if any is present during the encounters. The spacecraft's orbital mechanics will require it to use Callisto for gravitational shaping of its orbit, just as Galileo did. Unlike Galileo, however, Europa Clipper carries instruments specifically designed for the icy moon science investigations, and its Callisto flybys will return data of a quality that Galileo's opportunistic measurements could not approach. The magnetometer, the ice-penetrating radar reason, and the gravity science instrument aboard Europa Clipper will all contribute Callisto measurements that can be directly compared with the JUICE results, providing an independent dataset from an entirely different spacecraft and team. The two missions together will produce a cross-calibrated, mutually reinforcing body of evidence about Callisto's interior that will be robust in a way that neither mission could achieve alone. And then, on a longer horizon, Tianwen-4. China's planned mission to Jupiter, proposed for launch in approximately September 2029, would follow a trajectory involving Venus and Earth. Gravity assists before arriving in the Jovian system in approximately December 2035. The primary spacecraft would spend approximately 2 years conducting observations of Jupiter and its system before maneuvering into orbit around Callisto in approximately February 2038. The mission would make Tianwen-4 the first spacecraft ever dedicated to orbiting Callisto, not flying past it, not using it as a gravitational tool, but entering orbit around it and studying it from close range over an extended period. The orbital vantage point changes the science fundamentally. Flyby measurements capture a snapshot in time. An orbiting spacecraft accumulates data across many orbital periods, sampling the gravitational field and magnetic environment from every angle and at every phase of Jupiter's rotation, building up a complete picture that no collection of flybys can replicate. If Tianwen-4's Callisto orbit is confirmed and proceeds as currently proposed, the scientific return on Callisto's interior structure and surface composition by the late 2030s will dwarf everything the Galileo era produced. The convergence of 3 independent missions, JUICE 21 flybys and radar mapping beginning 2031, Europa Clipper's Callisto encounter data beginning the early 2030s, and Tianwen-4's orbital mission, beginning approximately 2038, represents an extraordinary concentration of scientific attention on a moon that spent 60 years as the solar system's most thoroughly dismissed large world. The missions did not develop in sequence because anyone suddenly decided that Callisto deserved priority. They developed because the orbital mechanics of exploring Jupiter required that spacecraft flying through the Jovian system interact with Callisto, and because each successive round of analysis from the Galileo magnetometer data in the 1990s through the Cochrane et al. 2025 reanalysis made the scientific case for Callisto's ocean stronger and more insistent. The mission attention followed the evidence, belatedly and somewhat accidentally, in the way that science often discovers that the thing it has been overlooking turns out to have been worth looking at all along. There is one more dimension of this mission picture that rarely receives attention in general accounts of outer solar system exploration: the question of why Callisto specifically, among the Jovian moons, is the natural first target for any future human presence in the Jovian system. The radiation environment at each of the Galilean moons is not uniform, It varies enormously depending on how deeply the Moon sits within Jupiter's magnetospheric particle belts. Io, the innermost Galilean moon, orbits well inside the most intense regions of Jupiter's radiation environment. Europa orbits within a zone of particle radiation so intense that a spacecraft maintaining close orbit around Europa rather than around Jupiter would accumulate a catastrophic dose of radiation within months, which is precisely why Europa Clipper is designed to orbit Jupiter and make rapid dives past Europa rather than lingering in Europa orbit. Ganymede orbits in a somewhat less intense radiation zone and has the partial shielding benefit of its own magnetic field, which deflects some of the incoming particles. Callisto orbits at approximately 26.3 Jupiter radii, well outside the main radiation belts, in a region where the particle flux from Jupiter's magnetosphere is approximately 300 times lower than at Europa. The radiation dose at Callisto's surface is approximately 0.01 rem per day, or approximately 0.1 millisieverts per day, above Earth's ambient surface dose, but orders of magnitude below what any human or robotic system would face at Europa or Io. This radiation advantage is not a minor operational convenience. It is a fundamental determinant of what kinds of infrastructure can exist at Callisto for how long. A robotic lander at Europa, designed for long-term surface operations, would accumulate a total ionizing dose that would destroy its electronics within a small number of years. A lander at Callisto could operate for decades without radiation becoming a limiting factor. A crewed surface habitat at Europa would require substantial mass dedicated to radiation shielding and would still impose a significant radiation health burden on any crew members residing there for extended periods. A crewed facility at Callisto, orbiting or on the surface, is a fundamentally different engineering problem, one where radiation is a consideration rather than a crisis, and where the total shielding mass required to protect human occupants is manageable by the standards of what future heavy-lift launch systems could realistically deliver to the outer solar system. NASA's long-term conceptual planning for human exploration of the Jovian system has, for precisely these reasons, identified Callisto as the most practical base of operations for a crewed mission to the Jupiter system, a staging point from which robotic systems could be remotely operated at Europa or Ganymede, close enough to manage communications with acceptable round-trip light times, far enough to keep crews out of the radiation belts that would otherwise make human presence in the inner Jovian system extraordinarily dangerous. There is a deep irony in this. The moon that was called the boring one, the ugly duckling, the hunk of rock and ice, the one that scientists treated for decades as a gravitational convenience rather than a scientific destination, turns out to be the most hospitable large body in the Jovian system for any human being who might one day want to be there. The qualities that made Callisto seem uninteresting, its distance from Jupiter, its isolation from the orbital resonances that drive tidal heating in the inner moons, its stable and unchanging character, are precisely the qualities that make it survivable. The quietness that the scientific community read as evidence of irrelevance is, from the perspective of anyone thinking about extending human reach into the outer solar system, evidence of opportunity. The moon that does nothing dramatic from the outside is the moon where you might actually be able to live. And from its surface, or from a facility in its orbit, you would look inward toward Jupiter and see Io erupting in the distance. Europa's fractured ice gleaming in the pale Jovian sunlight. Ganymede's grooved terrain visible as more than a point of light, the entire extraordinary family that overshadowed Callisto for 4 centuries, now framed against the swirling bands of the giant planet, with Callisto's ancient craters beneath your feet, serving as the foundation for everything that comes next. The missions approaching Callisto are not arriving at a solved problem. They are arriving at the first serious attempt to solve it. The 2025 Cochrane et al. Analysis changed the terms of the debate from whether Callisto's magnetic signature was worth taking seriously to how best to interpret a signal that most likely requires a subsurface ocean, but it did not close the bronze question. JUICE's arrival in the Jovian system in July 2031 and its first Callisto flyby shortly thereafter will begin the process of replacing the Galileo data's ambiguity with a dataset of substantially greater depth and rigor. Each subsequent flyby at each different orbital geometry will add constraints that the multi-frequency models can use to narrow the parameter space further. By the time JUICE has completed all 21 Callisto flybys, a process that will take several years as the spacecraft's tour of the Jovian system progresses before its final orbital insertion around Ganymede in 2034. The question of whether Callisto has an ocean will, in all probability, have moved from the category of well-supported hypothesis to the category of established scientific fact, one way or another. The 25-year wait that followed the Galileo era will be over. What replaces it will be a richer, stranger, and more demanding set of questions about what Callisto's interior actually contains and what it means for the broader understanding of ocean worlds in the outer solar system. The quiet moon at the edge of the Jovian family has been waiting for 4 billion years and for 60 years of scientific study, during which almost no one looked carefully at what it was doing inside. It will not have to wait much longer. And when the answer finally arrives, it will reshape not just what scientists think about Callisto, but how they think about every world that was quietly set aside because its outside seemed too unremarkable to warrant asking what might be happening within. Every scientific discovery has a provenance that includes not just the moment of finding, but the long accumulation of decisions that made finding possible, and equally, the accumulation of decisions that made finding delayed. The story of Callisto is, at its most fundamental level, a story about which version of delay gets written into the history of a discovery. There is the delay that was justified the years before instruments existed to measure the right things, before computational power existed to run the analyses, before the theoretical frameworks existed to interpret the measurements. And there is the delay that was not justified the years when the data existed, the instruments existed, the computing power existed, and the theoretical frameworks existed. But the decision to apply them to Callisto specifically was simply not made because Callisto had been categorized as not worth the effort. The 2025 Cochrane et al. Analysis falls almost entirely into the second category. The data that produced the strongest evidence yet for Callisto's subsurface ocean was collected between 1996 and 2001. The analytical approach that produced the result was conceptually available multi-frequency electromagnetic induction analysis within a few years of the data being collected. What was missing was not capability. What was missing was priority. And priority was absent because Callisto had been called the ugly duckling and the label stuck. This is not a comfortable observation, and it is not meant as a criticism of any individual scientist or any individual mission team. Every scientist working in planetary exploration during the Galileo era, was making priority judgments under severe resource constraints, and those judgments were, by any reasonable assessment, defensible. The decision to focus the detailed Galileo analysis on Europa and Io and Ganymede was not wrong. It was appropriate given what was known at the time, and it produced extraordinary science at each of those targets. The point is not that someone should have worked on Callisto instead of Europa. The point is that the history of Callisto's magnetic field data illustrates something about how science actually works at the institutional level, how categorization operates as a filtering mechanism, sorting questions into the queue and out of the queue based on assessments of scientific promise that are themselves products of existing assumptions about what is interesting. Callisto's magnetic field data was in the queue from the moment it arrived on Earth. It stayed in the queue, largely unadvanced, for over 20 years because the Moon was already categorized as a background character in a story about more dramatic worlds. The lesson is not unique to planetary science. It appears in every field where the supply of interesting problems exceeds the supply of scientists and instruments and funding to investigate them, which is to say, it appears in every field. The problems that get worked first are the ones that are already framed as interesting. The problems that wait are the ones whose framing has been settled in a way that suppresses the interesting question underneath. Callisto's framing archetype of quiescence, dead world, gravitational stepping stone, suppressed the question of what its magnetic field was measuring for more than 20 years. What changed in 2025 was not the problem, it was the reframing. Someone decided to look at all 8 flybys simultaneously. Someone decided that the multi-frequency approach was worth applying to a question that had been sitting in the file for decades. And the data, which had never stopped being the data, finally had a question asked of it that it was capable of answering. This is worth sitting with for a moment, because it carries implications that extend well beyond Callisto. The Solar System's archives, the data held by NASA, by ESA, by JAXA, and other space agencies, accumulated across 50 years of planetary exploration, contain measurements from dozens of bodies that received a flyby or a single mission and were then set aside as understood or as insufficiently interesting to warrant follow-up. Many of those assessments were almost certainly correct. Some of them were almost certainly not. The Callisto case demonstrates that the critical determinant of whether a reanalysis produces a significant result is not primarily the quality of the original data, it is the framing of the question that is asked of the data. The Galileo magnetometer data collected at Callisto was as good as the instrumentation of the time could produce. It was fully capable of constraining the ocean hypothesis if analyzed with the multi-frequency approach. It waited not because it was inadequate, but because no one asked the full question of it until 2025. How many other archives contain datasets that are fully capable of answering important questions if only someone asks those questions of them? That is not a rhetorical question. It is a research program. The question of Callisto's habitability is the one that will define how the Moon is understood for the next generation of scientists, and it deserves careful framing. Habitability is not a binary property. A world is not either habitable or uninhabitable in the way that a light switch is either on or off. Habitability is a gradient of conditions that ranges from environments where life, as we understand it, is essentially guaranteed to arise given enough time, through environments where life might arise under some conditions but not others, to environments where life is essentially excluded by the chemistry or the physics of the place. Callisto's potential ocean sits somewhere in this gradient, and where exactly it sits depends on questions that current data cannot answer. If the ocean lacks contact with the rocky seafloor, if it is trapped between ice above and high-pressure ice below, without access to silicate minerals and the chemical gradients that water-rock reactions create, then it is a chemically impoverished environment by the standards of what life on Earth requires. The energy available from ice-water interactions and from whatever organic material was incorporated during accretion is real but limited, and 4 billion years of isolation from mineral surfaces would leave the ocean in a chemical steady state from which the emergence of self-replicating chemistry would face very high barriers. If the ocean does contact the rocky seafloor, if the ice shell is thin enough and the ocean deep enough to have maintained contact with the silicate interior throughout Callisto's history, then the situation changes substantially. Long-lived radiogenic decay of potassium-40, uranium, and thorium in the silicate component releases heat continuously and will continue doing so for billions of years into the future. That heat drives serpentinization and other water-rock reactions that generate hydrogen and a suite of reduced chemical compounds. The chemical gradients between those reduced compounds and the oxidized species in the overlying water column create energy sources that microbial life on Earth exploits at deep-sea hydrothermal environments and in the basalt aquifers beneath the ocean floor. If those gradients exist at Callisto's seafloor, they have been operating continuously for approximately 4 billion years without the thermal disruption that tidal heating imposes on Europa's interior. The chemical environment would be older and more chemically evolved than Europa's ocean, accumulated rather than continuously churned. The astrobiological implications of this stable, ancient chemical environment are genuinely ambiguous rather than straightforwardly positive or negative. Life on Earth has persisted through billions of years of geological activity, mass extinctions, continental reconfiguration, and periodic catastrophic events. Its tenacity and adaptability over that span is extraordinary. But the origin of life, the initial emergence of self-replicating chemistry from an environment of complex but non-living molecules, appears to have been driven, in part, by the dynamic processes that created concentration gradients, energy flows, and physical mixing. Hydrothermal vents at the seafloor of the early Earth, alkaline chimneys that generated proton gradients across mineral surfaces, tidal pools that concentrated organic molecules through cycles of wetting and drying. These dynamic environments are among the leading candidates for where life originated, precisely because they were energetically active and chemically diverse. A stable, cold, chemically isolated ocean might maintain an energy gradient sufficient to sustain life once it originated, but whether it would provide the conditions for life to originate in the first place is a harder question. This uncertainty is not a failing of the science. It is an accurate description of where the science is. The origin of life is not understood well enough on Earth from the single example we have to confidently predict whether a specific set of conditions elsewhere would or would not be sufficient to produce it. The honest scientific position on Callisto's habitability is that the Moon cannot be excluded from the category of potentially habitable worlds, that the conditions that might exist at its ocean floor are in the range of conditions that planetary scientists take seriously as potential hosts for life, and that confirming or ruling out habitability requires measurements that have not yet been made. The missions now traveling toward Jupiter will narrow the physical picture, the ocean depth, the ice shell thickness, the degree of water-rock contact, but they will not directly sample the ocean, and they will not answer the biological question. That answer, if it ever comes, requires a mission that has not yet been designed, let alone built or launched. What the coming decade of missions will answer is the physical infrastructure question. Is there an ocean? How thick is the ice above it? Does the ocean reach the rock below? What is the temperature at the interface? What chemicals are present in the ice shell near the surface? These physical answers will enable scientists to build much more informed models of what the ocean environment is like, and from those models to make much more specific assessments of whether the conditions fall within the range that any life chemistry could plausibly exploit. That is meaningful progress, even though it falls short of the ultimate question. And it is progress that would not be happening at all if the 2025 reanalysis had not moved Callisto from the category of ambiguously uncertain to the category of very likely an ocean world. The reanalysis changed what questions the planetary science community is now asking about Callisto, and changed the scientific priority that those questions carry. It is the reframing that makes the missions matter more, not just the missions themselves. There is a further dimension to Callisto's story that belongs specifically to this final chapter, because it requires the kind of perspective that only the full accumulation of the story allows. The question of what Callisto represents in the broader taxonomy of ocean worlds, and why that representation matters for how we think about liquid water in the outer solar system. Before the Galileo mission, the prevailing view was that liquid water oceans in the outer solar system were a specialized phenomenon driven by specific and unusual mechanisms. Europa's ocean was driven by tidal heating from its orbital resonance with Io and Ganymede, a specific orbital configuration produced by Jupiter's gravity. Enceladus, Saturn's small moon, had active geysers driven by tidal heating from its orbital resonance with Dione. These were understood as exotic special cases, bodies where the specific geometry of their orbital situation created an exceptional energy source that most worlds in the outer solar system lacked. The implication was that most icy bodies in the outer solar system were frozen through, their interiors long since congealed into solid mixtures of ice and rock without any sustained liquid zone. Callisto challenges this picture at its foundations. Callisto has essentially no tidal heating. It is not in a meaningful orbital resonance with any of the other Galilean moons in the way that Io, Europa, and Ganymede are locked into the Laplace resonance. It experiences only a weak and variable 3 to 7 relationship with Ganymede that contributes negligible heat to its interior. Its internal heat budget is dominated not by tidal energy but by radiogenic decay, the same heat source that operates inside every large, rocky, or icy body in the solar system that contains silicate material. If Callisto has maintained a liquid ocean on radiogenic heating alone for 4 billion years without tidal heating, then the energy threshold for maintaining an ocean in a large icy body is lower than the pre-Galileo picture suggested. And if the threshold is lower, then the number of bodies in the outer solar system that might have maintained oceans, large Kuiper belt objects, dwarf planets in the trans-Neptunian population, the icy moons of Uranus and Neptune that have been visited only once by Voyager 2 in the 1980s and are largely uncharacterized, increases substantially. Callisto, in other words, is not just an ocean world candidate in its own right. It is a calibration point for how common ocean worlds might be in the outer solar system. If the presence of radiogenic heat in a large icy body is sufficient to maintain a liquid layer and Callisto's ocean, if confirmed, would demonstrate that it is then the outer solar system may be populated with subsurface oceans far more widely than tidal heating alone would produce. The moons of Uranus, ranging in size from Miranda at roughly 470 kilometers radius to Titania and Oberon at roughly 790 and 760 kilometers radius, all contain silicate material in their interiors and have been orbiting for the age of the solar system. Whether any of them maintain subsurface oceans is entirely unknown. The answer to that question depends critically on the minimum heat flux required to prevent an ocean from freezing, which in turn depends on how thick and how conductive the ice shell is, and whether antifreeze compounds, like ammonia, are present to lower the melting point. Callisto's ocean, if confirmed, provides the most direct observational constraint on that minimum heat flux that any outer solar system body has yet provided. It sets the floor. Everything above the floor, in terms of size and radiogenic heat content, is a candidate. This is the deepest significance of the Cochrane et al. 2025 finding, one that extends well beyond the question of whether Callisto specifically hosts life or provides a future base for human operations in the Jovian system. It is the significance of a calibration point in a problem domain where calibration points are desperately scarce. We have exactly one confirmed example of a world on which life originated and persisted: Earth. We have a small and growing number of worlds where the physical conditions for liquid water have been established or strongly inferred: Europa, Ganymede, Enceladus, Titan, and now Callisto, with the strongest evidence yet produced for the last of these. Each additional world in that list narrows the uncertainty about what the minimum conditions for liquid water in the outer solar system are, and therefore narrows the uncertainty about how many worlds there might be that we have not yet characterized. Callisto's inclusion in the list, if JUICE confirms it as expected, extends the lower boundary of what counts as a survivable heat budget for a subsurface ocean further down into the range accessible by radiogenic heating alone. And that has consequences for every assessment of the outer solar system's habitability potential that anyone will make for the next several decades. The 400-year history of Callisto's relationship with science ends, or rather, enters its next phase at a moment of genuine transition. The moon that Galileo discovered on January 7th, 1610, as the outermost and most stately of four unexpected points of light near Jupiter, that was photographed for the first time in close-up by Voyager 1 in March of 1979, that received its 8 dedicated encounters from Galileo between 1996 and 2001, that was called the Ugly Duckling and the Hunk of Rock and Ice and the Archetype of Geologic Quiescence, and that had its magnetic field data reanalyzed in 2025 to produce the strongest evidence yet for a subsurface ocean. That moon is now the target of more active scientific attention, more mission resources, and more carefully formulated questions than at any previous point in its 4-century relationship with human curiosity. The history of science is populated with objects that turned out to be more interesting than their first appearance suggested, and with fields that turned out to contain depths that early categorization foreclosed. But few examples are quite as complete as Callisto's, a world that was present at the moment, that revealed moons orbit other planets, that spent 4 centuries in a hierarchy defined by comparison to its more immediately dramatic siblings, that recorded a 4 billion-year interior story in a magnetic signal that sat in an archive for 25 years, and that now sits at the convergence of 3 independent spacecraft missions that will finally answer what it has been trying to say. The craters preserve the outside, the magnetic field preserved the inside, the archive preserved the data. The question was always there. What changed, finally, is that scientists asked it carefully enough to begin hearing the answer. Whatever JUICE magnetometers and gravity instruments tell us about Callisto's ocean beginning in 2031, whatever Europa Clipper's Callisto encounters add to the picture, whatever Tianwen 4 eventually reveals from Callisto orbit, beginning in approximately 2038, the answer will not be a simple yes or no. It will be a constrained range of physical conditions that then requires decades more of theoretical and observational work to fully interpret. The ocean question will be answered or very nearly answered. The habitability question will remain open. The chemical question will deepen rather than resolve. That is how science works when it finally arrives at a problem. It has deferred too long. The answer to the first question always opens a door to a harder one. Callisto's door has been closed for 4 billion years. The keys have been on their way since April 2023, when JUICE left Earth aboard its Ariane 5 rocket and began the 8-year journey to Jupiter. The first knock will come in 2031. And whatever answers Callisto gives in response will be worth every year of the wait, every year of the necessary wait, and every year of the unnecessary wait that came before it. The universe holds its secrets patiently, and the patient ones are sometimes the ones worth finding. Sleep well, stargazer. The ancient, silent moon at the edge of Jupiter's family has been keeping its secret for 4 billion years, and it will still be there, waiting when you wake. The philosophical dimension that belongs to Part 4, reserved specifically for this chapter, as the repetition prevention protocol requires, is this. The history of how Callisto was treated reflects something genuine about the cognitive architecture of science that is worth naming directly, because naming it is the only way to avoid repeating it. Science is a human enterprise conducted within human institutional structures, and human institutional structures allocate attention according to existing categories of importance. Those categories are not wrong. They are not arbitrary. They emerge from genuine assessments of promise, shaped by the data available at the time they are made. But categories have inertia. Once something has been placed in the category of understood, or unimportant, or background, the inertia of that placement resists revision. The Callisto case is instructive precisely because the category dead world archetype of quiescence was not even a strongly negative assessment. It was simply a deprioritization. Callisto was not viewed as a scientific problem to be solved. It was viewed as a context in which other problems were set, and that framing, once established, persisted for decades longer than it should have, because no single piece of evidence was dramatic enough to override it. There was no eruption, no geyser, no plume, no freshly fractured surface demanding immediate attention. There was just a magnetic signal sitting in an archive, gradually building its case, waiting for someone to develop both the analytical tools and the motivation to apply them. The motivation arrived in the mid-2020s as a convergence of several factors. The JUICE mission, already in transit toward Jupiter by 2023 when it launched, created institutional momentum for the kind of preparatory science that requires knowing in advance what questions the mission will be designed to answer. JUICE was designed with Callisto as a significant secondary target. 21 dedicated flybys is a substantial investment for a secondary target, and that design commitment created reasons for the science community to revisit what was known about Callisto and what remained uncertain. The Cochrane team at JPL was precisely the kind of work that preparatory science generates, a careful reanalysis of existing data using tools and approaches that had matured since the original data was collected, specifically in preparation for the richer dataset that JUICE would eventually produce. In this sense, the 2025 result is not purely the outcome of belated attention to a neglected archive. It is partly the outcome of a spacecraft already launched and already on its way, creating the scientific incentive to establish what the archive says before the new data arrives. The mission context changed the priority of the question. This is a genuinely hopeful observation about how science can work even in the presence of the category inertia problem. A committed mission to a target creates institutional reasons to investigate that target more thoroughly, even for questions that had previously been deprioritized. JUICE's commitment to 21 Callisto flybys created the context in which reanalyzing the Galileo data became worth doing. And the result of that reanalysis substantially strengthened the case for the scientific investment the mission is making. This is the positive feedback loop that the Outer Solar System Exploration Program has been running since the Voyager era. Each new commitment to explore generates preparatory science that deepens the questions, which in turn justifies the commitment, which in turn enables the exploration. Callisto's current moment in this cycle is the most intense it has ever been, and the result a moon that was treated as a gravitational convenience for decades, now receiving sustained, serious, multi-mission attention, represents the completion of a cycle that started with Galileo's magnetometer data in 1996. It is worth dwelling on what the next cycle might look like after JUICE and Europa Clipper and Tianwen-4 have completed their work. If Callisto's ocean is confirmed, and the balance of current evidence makes that confirmation the most likely outcome, the question of what to do about it becomes immediate in a way that it is not today. Confirming an ocean does not confirm habitability, but it changes the scientific and public framing of Callisto permanently. The moon that everyone forgot, the moon that was called a hunk of rock and ice, becomes a body that has maintained liquid water for 4 billion years. And once that framing is in place, the pressure to design a mission that can investigate the ocean more directly, one with an ice-penetrating probe capable of reaching the ocean's surface, or a lander equipped with geochemical instruments to sample surface material that might contain ocean-derived chemistry, will be substantial. The surface of Callisto, remember, is not a barrier to the ocean in the way that its depth suggests. The processes of sublimation and irradiation that have been working on the surface material for 4 billion years may have driven some degree of chemical exchange between the interior ice and the surface. On Europa, where the ice shell is much thinner and resurfacing is active, scientists have proposed that ocean material is periodically brought to the surface, where it can be sampled by a spacecraft without the need to drill through kilometers of ice. On Callisto, with its thicker, quieter ice shell, any such exchange is expected to be far slower and far less complete. But it is not zero. The irradiated surface material on Callisto, the carbonaceous compounds, the sulfur species, the processed organic molecules, carries a chemical record that instruments sophisticated enough to read it might find informative. A future lander at Callisto would not be sampling the ocean directly, but it would be sampling the product of 4 billion years of slow chemical interaction between the interior and the surface, and that record, if legible, might tell scientists something about what is happening deep inside the world that no orbital measurement can access. The timeline for such a mission is entirely speculative from the current vantage point. The inner solar system is currently absorbing the bulk of the planetary science budget. Mars sample return, lunar exploration, Venus investigation, and the outer solar system program is advancing on the timescales that the long cruise times and high launch costs of Jupiter and Saturn missions impose. A Callisto lander mission, if it were proposed today, would not be expected to arrive at its target for at least 15 to 20 years after launch, which puts any realistic surface mission to Callisto in the 2050s at the earliest. But the scientific case for such a mission, which does not yet fully exist because the ocean has not yet been confirmed, will begin to be built in earnest as JUICE's Callisto flyby data arrives beginning in the early 2030s. If that data confirms the ocean, the mission concept development will accelerate. If it confirms ocean rock contact, the astrobiological motivation will become central to the argument. This is how the outer solar system exploration program builds. Each confirmed finding creates the scientific justification for the next investigation, and the investigations move outward in confidence and specificity as the evidence accumulates. The 4-century arc of Callisto's relationship with science is, in this light, not an arc of neglect and eventual redemption. It is an arc of gradually deepening question. The question that Galileo asked, "What are these points of light near Jupiter?" was answered within weeks. The question the Voyager team asked, "What does the surface of Callisto look like in detail?" was answered in 1979. The question the Galileo mission asked, "What is the magnetic and gravitational structure of Callisto?" was answered partially, with the ambiguity that the instruments and analysis methods of the 1990s could not fully resolve. The question that the Cochrane team asked in 2025, "Is the magnetic induction signal at Callisto best explained by an ocean or by an ionosphere alone?" has now been answered to a high degree of confidence by an ocean. The question that JUICE will ask beginning in 2031, "What are the precise properties of that ocean and how does it relate to the interior structure?" will be answered over the following years with a precision that the earlier investigations could not approach. And the question that will remain unanswered after all of this, "Is there anything alive in that ocean?" is the one that a generation of scientists not yet born will inherit. This is the normal condition of science on the frontier. Not final answers, but better questions. Not conclusions, but constraints that rule out the wrong answers and narrow the space in which the right one lives. Callisto has been providing constraints for 4 centuries. The constraints were ignored for most of that time because the world had been categorized as not worth constraining carefully. The realization that the constraints were actually pointing towards something significant, that the magnetic signal was real, that the interior was genuinely anomalous, that the surface was thermally complex in ways that standard models could not accommodate, is the realization that Part 4 of Callisto's story represents. The first 3 parts were written in the language of accumulating evidence and missed opportunity. This final part is written in the language of beginning, of missions launched and en route, of analyses completed and peer-reviewed, of questions that have finally been formulated precisely enough that instruments can be designed to answer them. The ancient, crater-covered, magnetically restless, thermally complex, apparently undifferentiated, very likely ocean-bearing, most hospitable for humans, most overlooked, most patient moon in the Jovian system is no longer the background character in someone else's story. It is the subject. The question it has been waiting to answer is being asked at last. with the seriousness it deserves. And whatever the answer turns out to be ocean confirmed, ocean characterized, life possible, or life implausible, or life undetermined, the act of asking it carefully, after 400 years of looking past it, is, itself, the most important thing that has happened to Callisto since the night in 1610, when a man in Padua wrote down a point of light near Jupiter and did not yet know what he was truly looking at.